The size of space objects is mind-boggling. Sometimes it is hard to believe that some barely visible dots scattered across the night sky could be giant balls of glowing plasma capable of engulfing entire planetary systems. Some of them are hundreds and thousands of light years away from Earth, while others are very close by cosmic standards. And today, we're going to the most prominent of these stars. Our fantastic virtual journey will begin with the most important star for us, the Sun. Then we'll explore several nearby stars before traveling deep into the galaxy to a blazing monster hidden among clouds of interstellar dust. The next stop on our way will be Betelgeuse, pulsing in agony, a star that may burst into a deadly supernova at any moment. Leaving the dying star behind us, we'll travel to a true giant, capable of swallowing tens of millions of stars like the Sun, CW Leonis. Then an even more impressive star is waiting for us, the majestic supergiant Stephenson 2-18, which is the largest known star in our galaxy. And at the end of the journey, we'll travel to the stellar nursery of the Orion Nebula and observe how such cosmic monsters are born. Let's get ready, and we begin. To begin with, the Sun is a main sequence star whose age is approximately 4.6 billion years. It currently falls into spectral class G2V, which on balance makes it a typical yellow dwarf. The Sun's surface temperature is about 5,800 Kelvin, which is 5,530 degrees Celsius, but it should be mentioned that there are both colder and hotter areas to be found on it. Incidentally, the star's inner layers and its outer corona are as scorching hot as millions of degrees. But for all that, they barely contribute to the visible radiation. The Sun's average diameter equals around 1.4 million kilometers, which is 109 times that of our Earth. As for the star's mass, it reaches 2 times 10 to the power of 30 kilograms, or 333,000 times that of the Earth, and actually accounts for 99.9% of the mass of the entire solar system. We're used to seeing the Sun as small, but in fact it is larger and brighter than 80% of all the stars in our galaxy that we know of. Hydrogen accounts for 92% of the Sun's overall volume. In one of our previous videos on stellar evolution, we mentioned that it is mainly this gas that fuels thermonuclear reactions for the overwhelming majority of stars when its temperature reaches incredibly high values. As they merge, hydrogen nuclei release great amounts of energy and transform into helium, which gradually accumulates in the star's center. At the moment, helium accounts for 7% of the Sun's volume and 25% of its overall mass. In addition to helium, stellar matter contains other elements as well, like carbon, oxygen, nitrogen, and iron, but their percentage is quite negligible. The Sun has an elaborate structure and is made up of several layers which differ in their properties. A massive core is at the center of the star. Estimates show its diameter to measure 25% of the Sun's overall size. The core's temperature measures as much as 14 million Kelvin, while 1 cubic meter of the material weighs around 150 tons. It is here that thermonuclear reactions, the source of energy for our star's luminosity, run their course. Every second, approximately 4.26 million tons of stellar matter is transformed into luminosity as a result of these processes. The core is surrounded by the so-called radiation zone, which continues to the point of 0.7 the Sun's radius. The density of matter in this area is too great for it to get mixed up thoroughly, and thus to carry heat to the upper layers of the star. That is why the way energy is transferred here is this. Particles of stellar plasma are continuously absorbing photons and radiating them again. Mathematical modeling shows that the temperature in this part of the star dramatically changes from 7 million Kelvin in its depth to 2 million Kelvin on the outer boundary. Estimates reveal that a quantum of light produced by the core may stay in the radiation zone from 10,000 to 170,000 years, and only then to move on to the next layer of the Sun. The one lying above, known as the convection zone, forms the Sun's outermost layer and is comparatively dense. Stellar matter here is more rarefied and changeable, which gives rise to enormous vortices in the convection zone. These vortices carry hot plasma from deeper regions of the layer to the star's surface, as it were, while plasma masses from the outermost areas, slightly cooled, move down. These convection cells remain stable for 10 to 15 minutes, after which they get destroyed to give rise to new vortices again. This continuous movement of matter creates a magnetic field, which pervades the entire inner part of the solar system. The Sun is also surrounded by an atmosphere. It is made up of several layers of elaborate structure. The lowest one is called photosphere. This area emits most of the star's visible light, so when watching the Sun, it is actually this photosphere that we see. As for its thickness, it measures from 100 to 400 kilometers, with a temperature fluctuating between 6600 and 4400 Kelvin, or between 6330 and 4130 degrees Celsius. Higher up lies a more rarefied area around 2000 kilometers thick, known as the chromosphere. It can be observed from the Earth at the time of a total solar eclipse, or else by employing special equipment. This area is extremely hot, with the temperature fluctuating between 4000 Kelvin and 20,000 Kelvin. Interestingly, its outer border is covered with spicules, continuously active jets of hot gas spurting up a staggering 5,000 to 10,000 kilometers high. The uppermost area of the Sun's atmosphere is called the corona. It consists of giant prominences, flares and emissions that may reach 1 million kilometers in size. The matter making up the corona is remarkably rarefied and incredibly hot, with an average temperature of 1 to 2 million Kelvin and the peak at 20 million Kelvin. It is this area that is occasionally crossed by the Parker probe, and every time the spacecraft immerses deeper and deeper into the blazing abyss. Calculations of the energy flow released by the photosphere will show it to be insufficient to heat the chromosphere and corona to such mind-boggling temperatures. This means that there are some physical phenomena concealed in the Sun that we have not yet discovered, which additionally heat up the upper layers. There are several scientific hypotheses that attempt to account for this thermal paradox. According to one of them, the chromosphere and the corona gain additional energy by dispersing magnetic shock waves. Another assumption explains it as an effect of charged particles' acceleration in the star's exceptionally powerful magnetic field. The Parker Solar Probe was specially designed in order to get to the bottom of these phenomena and to study obscure processes in the upper layers of the Sun's atmosphere. This probe is part of NASA's project known as Parker Solar Probe, launched back in 2009. 9 years later, on the 12th of August 2018, Parker took off from the surface of our planet on its one-way journey to the Sun to fulfill its mission. However, before getting that far, it had to execute a number of maneuvers to enter the desired orbit. By using Venus's gravity, Parker slowly adjusted its trajectory, drawing ever so closer to the scorching blazing ball in the center of our system. It was ready to withstand the star's searing heat. The probe had been designed with a heat shield, and all the equipment had been made with a view to extreme conditions to be faced. Besides, Parker's calculated orbit is supposed to lie in the Sun's immediate proximity for a comparatively short time, after which it pulls back and has a chance of giving out heat to space. This alleviates effects of thermal exposure. The probe's main task is to define the structure and dynamics of the magnetic fields in the Sun's immediate proximity. Also, Parker is supposed to gauge the energy flow emitted by the star, to capture particles of stellar wind, and to register wave-like processes in the Sun's corona. As a side mission, The probe took photos of Venus and the comet Neowise as it was drifting towards our parent star. To deal with the missions successfully, the probe is equipped with a wide range of scientific instruments like photo cameras, instruments for capturing particles, magnetometers, as well as radiation and radio wave detectors. A number of factors toward this mission. In addition to critical temperatures, the measuring instruments are exposed to an extremely powerful flow of ionizing radiation. The Sun creates strong interference in the microwave range around itself, which means that transmitting the data collected by the probe to the Earth is no easy matter either. Still, the Parker probe is carrying on with its mission. With every completed spiral of its orbit, the distance to the star shortens. In late February 2022, it is to pass through the Sun's corona yet again, in order to collect a new portion of data. By 2024, the distance between the probe and the surface of our star will shrink to become an all-time short, just 6.5 million kilometers. Estimates show that when the probe is in its perihelion, its solar shield may heat up to 1,370 degrees Celsius, which is 3 times hotter than Mercury's sunny side and only slightly lower than the melting point of iron. Even now, the probe is whizzing at a speed of 163 kilometers per second in its perihelion, but it will eventually accelerate to 200 kilometers per second, which will make it the swiftest man-made space object made so far. The probe's life expectancy cannot be that long. On reaching the closest possible point to the Sun, Parker will manage to complete several orbits around it, which is supposed to take roughly a year. All this time, it will keep losing speed, and the scientific instruments on board will be exposed to extreme temperatures and powerful radiation. Eventually, they will all be out of order, and the probe itself will descend into the scorching depths of the Sun to be totally swallowed up by a fathomless ocean of blazing plasma. But before it happens, Parker will beam great amounts of useful data back to the Earth, which will help us make yet another step in space exploration. This is a potent proof that Parker's flight will not have been wasted. Having traveled 6 light-years away from the Sun, we will reach our first stop, a small red dwarf, designation GJ699, also known as Barnard's star. It is remarkable for its incredible travel speed across the sky, and also for the fact that it's capable of crossing the lunar disk in the course of 180 years. This is due not only to its close proximity to us, but also to its great proper motion. Barnard's star is moving towards the solar system at a speed of slightly over 100 kilometers per second and is going to become our closest star in about 10,000 years. By then, the distance between Barnard's star and our Sun will be just 3.8 light-years. But the red dwarf is so dim that it will not be visible even at such a small distance, and it will be possible to observe it only through optical devices. The star's mass is just 17% that of the Sun, and its radius is 6 times as small as that of our star. Just like all red dwarfs, Barnard's star is quite cool, with a surface temperature just 3,134 Kelvin, or slightly under 2,900 degrees Celsius. With these characteristics taken into account, it isn't surprising that the object's luminosity is 2,300 times lower than that of our parent star. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence for the presence of an exoplanet nearby. The calculations show it to be a cold super-Earth with a mass of not less than 3.2 times that of the Earth. The planet, named GJ699b, is located about 0.4 astronomical units from the center of the system and takes 233 days to complete a full orbit around its parent star. Unfortunately, the exoplanet follows an orbit that does not lie between the Earth and its parent star, so it's hardly feasible to carry out spectral analysis of the object. Still, mathematical modeling may give us some insights into what it's like. As Barnard's star is very dim, its planetary companion receives 50 times less energy than does the Earth from the Sun. That is why the temperature on the celestial body's surface is extremely low, just 105 Kelvin or 168 degrees Celsius below zero. However, it cannot be ruled out that tidal disturbances or radioactive decay may have released enough energy in the planet's interior to form a warm subsurface ocean. If that is the case, the potential life in its depths would have had ample time to gradually develop. For among the known stars, Barnard's star appears to be one of the oldest. According to estimates, its age is over 10 billion years, which is only a fraction of the expected lifespan of a star. As it is located quite close and is moving in a favorable direction, Barnard's star is one of the highest priority objects for a potential interstellar flight. Time will show if spacecraft launched from Earth will ever reach it. Meanwhile, on the other side of the Sun, there lies the almost exact opposite of the dim red dwarf. Of course, we're talking about Sirius, the brightest star in the night sky, which is 8.6 light-years away from our planet. From Earth, the star appears to be a single light source, but close inspection revealed that it is not a single object, but a binary star. The two components of the system are currently at their maximum distance from each other, about 30 astronomical units. The main star, also called Sirius A, is a bright blue and white star with a mass 2 times that of the Sun. At the same time, it is about 70% larger in diameter, and its surface temperature reaches 10,000 Kelvin. Because of this, Sirius A emits 25 times more energy than our Sun. The second object, known as Sirius B, is barely visible against the background of its bright and massive companion. It is a white dwarf with a radius of about 6,000 kilometers and a mass very close to that of the Sun. Like all stars of this type, its surface temperature is extremely high, reaching 25,000 Kelvin. However, due to its small size, this white dwarf is about 1,000 times dimmer than its stellar companion. After long and persistent research, no signs of planets have been found in the vicinity of Sirius. The reason for this may lie in the comparatively young age of the stellar system, or else the special position of the ecliptic plane. Because of this, the hypothetical exoplanets do not pass between the light source and the Earth, and therefore cannot be detected by the transit method. Another hypothesis claims that Sirius B exhausted its stellar fuel supply roughly 120 million years ago and transformed into a red giant. Soon afterwards, it shed its outer layers, turning into a compact and very hot white dwarf. As a result, the protoplanetary gas and dust disk enveloping the young stellar system at the time was destroyed by this explosion, its remnants scattered into the space around, denying the forming planets any chance of survival. Currently, both components of the system are moving around a common mass center in moderately elongated orbits, completing one every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, becoming brighter and more visible in the night sky. The minimum distance between us will be about 7.5 light-years, after which the system will start to slowly drift away from us. Things will go on like this for about another 660 million years, after which Sirius A will meet the same fate as its companion. For a brief moment, a massive flare will boost its luminosity by a factor of thousands, but within a few months, the star will fade completely, vanishing from the sky forever. Leaving the vicinity of Sirius, permeated by lethal ultraviolet radiation and stellar wind, we will perform a maneuver near the solar system to reach a small star 14 light-years from the Earth. It is designated differently in different catalogs, and one of its names is Wolf 1061. The star is a red dwarf with a radius of about 30% that of the Sun. Its mass is about 4 times smaller than that of our star, and its surface temperature is 3,272 Kelvin, or about 3,000 degrees Celsius. Like all objects in its class, Wolf 1061 is extremely dim. Its luminosity is only 0.14% that of the Sun, so the star is not visible to the naked eye from Earth. However, this red dwarf has one of the most abundant and diverse planetary environments of any stellar system near us. As many as 3 exoplanets have been discovered in its vicinity, all of them rocky and similar in composition to Earth. But still, conditions on each of the 3 celestial bodies differ considerably. The first and closest exoplanet to the parent star is called Wolf 1061b. It is located 0.038 astronomical units from the center of the system and completes a full orbit around it roughly every 5 days. The object has a mass in the range of 1.5 to 2 Earths and a radius 20% greater than that of our planet. It is likely that the celestial body is tidally locked and faces its star with one side at all times. For this reason, the temperature on the day side of the planet is extremely high, and the flares and stellar winds of the star so close to it virtually rule out any chance of there being an atmosphere. All these factors make the exoplanet completely unsuitable for the genesis and support of life. The second object in the system, Wolf 1061c, is located 0.089 astronomical units from its star and completes a full orbit around it roughly every 18 days. Thus, it is within the habitable zone of the star and can be considered a potentially habitable celestial body. Wolf 1061c is about 3 to 4 times more massive than our planet and belongs to the class of super-Earths. Observations show that its radius is about 1.6 times that of Earth, while the gravity on its surface is calculated to be 60% higher than what we're used to. The exoplanet receives noticeably less energy from its star than the Earth does from the Sun, so its temperature of equilibrium is much lower. It is 223 Kelvin, or about 50 degrees Celsius below zero, which is slightly higher than on Mars. Nevertheless, given variations in temperature during the day and from season to season, liquid water may well exist on the surface of the celestial body. With a dense atmosphere with a pronounced greenhouse effect, this probability is even higher, and conditions on the planet could approach favorable ones. Of all the potentially habitable exoplanets known to date, Wolf 1061c is one of the closest, ranking 5th on the list. The third object in the system is called Wolf 1061d. It follows a clearly elongated orbit, with the distance between the parent star and the aphelium reaching 0.73 astronomical units. As for the perihelion, it lies much closer to the system's center, just 0.21 astronomical units away. It takes the celestial object about 217 Earth days to complete a full year rotation. The mass of Wolf 1061d is calculated to be roughly 7.7 times that of our Earth. If this celestial body turns out to be a rocky object, its radius is supposed to measure about 1.7 times that of the Earth. If, on the other hand, this planet falls in the category of mini-Neptunes with a thick multi-layer atmosphere, its diameter is supposed to be not less than 2.2 times that of our planet. In spite of a comparatively high eccentricity of its orbit, Wolf 1061d never enters its star's habitable zone. The celestial body is likely to be completely unsuitable for supporting life, but may pose a great scientific interest in terms of planetary evolution. This system is one of top priority destinations for future explorations, and it is highly probable that there are new discoveries to be soon made in it. In addition to everything else, the star Wolf 1061 is also remarkable for its position, which is virtually at the very edge of the so-called local interstellar cloud. It is an area in space filled with hot but extremely rarefied hydrogen. Its temperature measures about 7,000 Kelvin, and on average there is just 0.3 of an atom to be found in 1 cubic centimeter of space here. It is about twice as little as the average value in the Milky Way. The solar system has been moving through the local cloud for the past 10,000 years. Its average diameter is about 30 light-years, but our system is almost at its very edge. Alpha Centauri, for example, is already in the neighboring so-called G-cloud. We, on the other hand, will spend about another 2,000 years within our cloud, after which we will enter an even thinner and hotter region. The local interstellar cloud was formed by the collision of two giant bubbles of hot cosmic gas. It has a momentum of its own, which is perpendicular to the direction of the solar system's motion, and also has a magnetic field and radiation. Fortunately, despite the high energy of the interstellar gas particles that make up the cloud, there is no threat to organisms on Earth. The solar wind is a reliable protection against cosmic hydrogen, and the Earth's dense atmosphere takes the hit of particles that do break through the heliosphere. Still, traces of the isotope Iron-60, also called interstellar iron, have been found in the ice of Antarctica. It is thought to have arrived to Earth from no other place but the local interstellar cloud. As we continue our journey through space, we will soon get to a rather unusual star called AP Columbae, located 27.4 light-years away from Earth. First and foremost, it draws our attention because it was born just 40 million years ago, when the dinosaurs would have long since died out on our planet. What is even more striking is that its birth took place in a completely different region of the galaxy, 450 light-years from the object's present position. Young stars usually remain close to their stellar nursery for quite a long period of time, up to several 100 million years. If you analyze the movement of AP Columbae, however, you will find that it probably previously belonged to the open cluster IC2391. The cluster has about 30 stars, united by a common origin and direction of movement. But a few million years ago, one of them exploded, shattering the delicate equilibrium of a multitude of cosmic bodies. This catastrophe gave the young star an additional momentum that swiftly expelled it from its birthplace. A very small red dwarf with a mass just 13% that of the Sun, this star emits 4 times more energy than any other known celestial body with the same parameters. In addition, its radius is twice as large as calculated based on the modern stellar structure theory. Strangely enough, another unusual feature of the star has helped to provide answers to these riddles. According to spectral analysis of its radiation, the stellar matter of AP Columbae contains an abnormally large amount of lithium. Normally, this element is found in abundance in protostellar clumps, but it burns out completely after the start of a thermonuclear reaction. This means that the star is very young and at the very beginning of its formation, not even in the main sequence phase yet. As a consequence, AP Columbae is unstable and explosive in nature. It is prone to violent outbursts and stellar matter ejections, during which its luminosity may increase by up to 10 times for a short while. Such events would normally threaten exoplanets nearby, stripping off their atmosphere and sterilizing their surface with ultraviolet radiation. As it is, observations show that there are no large space objects within 4.5 astronomical units of this star. In all likelihood, it is too young for the formation of fully fledged planets. Nevertheless, it is a unique cosmic body, very important for understanding early evolutionary stages of stars. As we've seen, not every star has a planetary system, so our next stop is near the orange dwarf Gliese 370, 37 light-years from Earth. In 2011, a single exoplanet was discovered near it, designated Gliese 370b. The object was discovered with the use of the radial velocity method and has a mass of 3 to 4 Earths. According to current understanding of the formation of celestial bodies, the discovered world is most likely a rocky planet, with a radius about 30% larger than the Earth's. Under such conditions, the gravity on its surface may be at least 40% higher than what we're used to. Gliese 370b is located at a distance of 0.26 astronomical units from its parent star and completes an annual rotation in 54.4 Earth days. Thus, the exoplanet is in the habitable zone of its star. If the albedo value of its surface is close to that of the Earth, then the average temperature of the celestial body should be about 25 degrees Celsius, which is a few degrees higher than on our Earth. The fact that an exoplanet is located quite far from its parent star suggests that it is not tidally locked and has its own diurnal cycle. This contributes to an evener distribution of heat over the surface of the celestial body, which as a consequence may create a milder climate. A moderately high gravity should smooth out the planet's terrain, which combined with an abundance of liquid water may cause vast seas to form, both warm and shallow. Such places have traditionally been considered the most comfortable for the genesis and support of life. At the time of its discovery, Gliese 370b was considered one of the most favorable exoplanets for potential biological life. However, more recent research has suggested that conditions on its surface are somewhat less attractive than previously thought. In particular, the atmosphere of the celestial body may be too dense and have a pronounced greenhouse effect. Still, even according to the most pessimistic predictions, the average temperature on the surface of the object does not exceed 78 degrees Celsius, which corresponds to a temperature range of about 30 to 100 degrees Celsius. Given that our planet's climate was about the same during the Archean period, Gliese 370b remains a very promising exoplanet for the search for extraterrestrial life, which means that its exploration must continue. If we stop and look around for a while, we will find that we have already traveled more than 50 light-years away from our solar system. There are over 1,000 stars within its radius, most of them single stars. Others are binary stars or even groups of stars. The most striking example is Castor, a complex and surprising system of as many as 6 components. This stellar system is located 50 light-years away from Earth and is visible to the naked eye as a single source of light. As the second brightest object in the constellation Gemini and the 23rd brightest in the night sky in general, Castor has been known to humans since ancient times. As the system has as many as 6 components, it has a rather complex structure. The 2 brightest of these, Castor A and B, are bluish-white Sirius-like stars, each with a red dwarf companion nearby. The distance between the mass centers of these binaries is about 110 astronomical units, and it takes them 445 years to complete a full orbit. About 600 astronomical units from Castor A and B, there is another compact binary system, consisting of a pair of almost identical red dwarfs. Each has a mass of about 0.6 times that of the Sun and has a surface temperature of about 3,900 Kelvin. The 2 stars are so close together that they take less than 20 hours to complete a rotation. They move around the system's common mass center following a very oblong elliptical orbit with an orbital period of about 14,000 years. So far, no confirmed exoplanets have been found in the Castor system. But if they do exist, they're most likely to be located here, near the faintest component of the system. In 2018, for example, astronomers detected variations in the orbital period of Castor C, which implies there may be a brown dwarf nearby, about 49 times more massive than Jupiter. According to calculations, it is located 14 astronomical units from the parent star and completes a full orbit around it every 54 years. It is possible that, like many red dwarfs, Castor C has rocky exoplanets close by. In this case, the skyline of such a hypothetical object must present a truly incredible spectacle. On one side, a considerable part of it is occupied by 2 crimson stars circling the sky without stopping, while on the other side, The eternal twilight is diffused by the light of a pair of stars, either of them hundreds of times brighter than the Earth's moon. Whether this is actually the case cannot yet be verified at this point. Temperatures of any star's interiors are incredibly high. It is hardly surprising, as thermonuclear synthesis, that is the main energy source of all stars, can take place only in these extreme conditions. When two atoms of hydrogen merge, they produce an atom of helium and release an electron and several neutrinos. In addition, a great amount of energy is released during the process. Still, the hydrogen-helium synthesis isn't the only process that heats up stars. At higher temperatures, other elements may take part in chemical reactions as well, for example lithium, carbon or oxygen. In this case, cores of heavier elements are produced, such as sulfur, magnesium or phosphorus. Their charge is higher and they repel each other more robustly. Much more energy is needed to overcome this resistance. When a main sequence star depletes most of its hydrogen supply, it starts to expand and cool off. With time, it ends up as a red giant. It will continue to burn due to thermonuclear reactions of helium transforming into carbon and oxygen. The lighter the star, however, the less time it will continue to burn. Eventually becoming unstable, it sheds its outer layers and goes supernova. This leaves it a white dwarf with no resources to fuel any thermonuclear reactions anymore. With all its energy sources depleted, it is forced to gradually cool off. Interestingly, when the mass of a star is higher than a certain value, heavy thermonuclear synthesis may become the star's main energy source even after all hydrogen has been used up. Such celestial objects are referred to as Wolf-Rayet stars. This class of space objects was discovered back in 1867 by the French astronomers Charles Wolf and Georges Rayet. The scientists' attention was caught by anomalously bright emission lines of heavy elements in these stars' spectra. As for the inner makeup of these unusual celestial objects, it was accounted for much later. Stars of this class are generally heavy. They have quite a meager supply of hydrogen and are in the final stages of their revolution. Wolf-Rayet stars are extremely rare. To date, just a few hundred of them have been discovered in our galaxy. As for their overall count in the Milky Way, it is estimated that there can't be over 2,000 celestial objects of this class. Wolf-Rayet stars are subdivided into three main sequences depending on the prevalent element in the spectrum: nitrogen, carbon and oxygen sequences. Each of them, in its turn, is subdivided into several types. As for the hottest star in the studied universe, it falls into the category of the oxygen spectral sequence ones. The celestial body, which is now known as WR102, was discovered back in 1971. At first, it was mistaken for the optical counterpart of the X-ray source GX3+1. However, further observations revealed that there were two completely different objects. According to data acquired thanks to spectral analysis, the discovered star had unusually bright oxygen lines in its radiation spectrum. Thus, in 1982, WR102 and four more bright stars became the first to form a new class. Spectral analysis showed that the star's surface temperature reaches over 210,000 Kelvin. This makes WR102 approximately 36 times as hot as our Sun. The luminosity of this scorching hot object is unbelievable. It is estimated at over 380,000 times that of the Sun. WR102 lies about 10,000 light-years away. The star is located in the part of the sky with the constellation Sagittarius. Incidentally, in spite of its exceptionally high luminosity, it can't be seen with the naked eye, as it is too far away from us. WR102 currently belongs to the extremely rare star class WO2. Containing great amounts of oxygen and almost no hydrogen, it mainly relies on the merging of heavy cores of such elements as neon, carbon and oxygen as its sources of energy. To date, only 9 objects of this class have been discovered, with 4 of them located in the Milky Way and the other 5 in other galaxies. There are 2 factors that make oxygen spectral sequence stars rare. Firstly, there are very few of Wolf-Rayet stars around because only stars with a mass not less than 40 solar masses are potential candidates to become ones. Secondly, this class represents the final stage of evolution of stars of this type. The stage may last anything from 1,000 to 10,000 years, which is mere seconds in astronomical terms. Being of comparatively modest dimensions, WR102 is notably quite a dense star. With its radius measuring just 58% that of the Sun, its mass, on the other hand, is estimated at 15 to 18 solar masses. On its birth, it is thought to have been as heavy as 40 to 60 solar masses. Still, the high temperature and robust chemical reactions in the star's interior cause an exceptionally powerful stellar wind, whose particles' velocity is over 5,000 km per second. It takes WR102 just a few months to lose 1 Earth mass worth of material on account of its stellar wind. At this rate of particle emission, the star is going to lose 1 Sun mass worth of material in the course of 10,000 years. There are no planets orbiting WR102, but it is shrouded in a gas envelope. Not dense and exposed to powerful ultraviolet radiation and strong stellar wind, the envelope gets contracted and ionized, which sustains its elaborate structure of protuberances and arches all around the star. According to a proposed theory, the gas cloud around WR102 may probably be remnants of the former hydrogen outer layer of the star. Another theory maintains that the cloud came to be as a result of the particle flow emitted by the star. WR102 is not the only outstandingly blistering place in the universe. For example, WR142, WR30A and WR93b, as well as the central star in the Bug Nebula NGC 6302, are as hot as around 200,000 Kelvin. Some white dwarfs may have almost the same surface temperature. However, all these are no match to neutron stars. When neutron stars are born, their temperatures may reach a staggering 100 billion Kelvin. Active neutrino emissions cool them off comparatively rapidly. But either way, the surface temperature of any neutron star is never less than a few 100,000 Kelvin. As for their cores, they must, admittedly, be hotter still. Having said that, it is highly improbable that the ultimate temperature record is ever going to be beaten. According to today's cosmological concepts, the temperature of the universe at the moment of the hypothetical Big Bang was approximately 1.4 times 10 to the power of 32 Kelvin. A fundamental physical constant, this value is referred to as the Planck temperature. Contemporary physics is not capable of defining a substance of a higher temperature, as physical laws are distorted beyond any recognition in such incredibly harsh conditions, quite beyond our imagination. Getting back to WR102, judging by the data we have on stellar evolution today, this star is in its autumn years now. As opposed to main sequence stars, Wolf-Rayet stars do not expand in their final stages of life. Their substantial mass holds all the star's material together in a dense and hot ball. However, after losing a lot of its mass through stellar wind, the object will eventually get destabilized. If current estimates are accurate, WR102 appears to be ready to go supernova at any point in the next 1,500 years. Bearing in mind that the distance between the star and the Earth is 10,000 light-years, it is highly likely that the event has already taken place. A supernova would have been accompanied by an extra powerful gamma-ray flare. Fortunately, our planet is too far away to suffer any pernicious effects of this dangerous emission. WR102 is comprised of rather heavy chemical elements and even iron. Its later evolution will force it to contract to a critical point. The great explosion bringing the star's life cycle to a close will unleash processes of robust proton and neutron capture. This way, still heavier elements form, including transuranium ones. Eventually, WR102 will be replaced by a neutron star, a celestial body unbelievably hot and dense. The former star's outer layers, disrupted by the explosion, will form a nebula. Slowly cooling off, it will give off heat to the space around it. Many billions of years later, this material will be able to form a new planetary system. The end of 2019. Astronomical observatories report a sudden decrease in the luminosity of the star known as Betelgeuse. Observations show that its luminosity dropped to 36% of the standard value within a matter of a couple of months. Some scientists are talking about an upcoming supernova, which will be the brightest object in the night sky. Disturbingly, the gamma-ray flow emitted by the explosion is thought to be potentially dangerous for life on our planet. April 2020. Astronomers assure the general public that Betelgeuse has recovered its luminosity to the standard value. It may still go supernova at any moment, but there is no way to predict this event with any degree of certainty. Assumptions about reasons for such anomalous fading are put forward. According to the most popular hypothesis, it was caused by a giant cloud of gas and dust ejected by Betelgeuse in the direction of the Sun very recently. June 2021. The assumption is confirmed by data from Earth-based telescopes. Astronomers keep observing the object, while astrophysicists model out the processes occurring in its interior. Before we attempt to get to the bottom of what was taking place, it's a good idea to be aware of what Betelgeuse is like. This object falls into the category of red supergiants and is in the final stage of its life cycle, according to today's theory of stellar evolution. With its luminosity and radius constantly changing, its outer layers are highly unstable. The star regularly emits millions of tons of scorching gas into space, and this forms gargantuan prominences. As they cool off, they contribute to the gas nebula surrounding Betelgeuse. The star's mass is around 17 times that of the Sun, and its diameter has by now been gauged only roughly at 700 to 880 times that of the Sun. Hypothetically, if Betelgeuse were to be placed in the center of our system, it would swallow up all the planets as far as Mars, as well as most of the asteroid belt. It should be mentioned that the star has no clearly defined edge because its outer layers are extremely rarefied. Besides, the object is shrouded in a gargantuan gas nebula made up of cooled-off prominences or protuberances and particles of stellar wind. At the same time, the density of stellar matter on the conventional edges of the star is only slightly higher than that of the nebula. Betelgeuse is a remarkably bright star. Its minimal luminosity is 90,000 times higher than that of the Sun, while its maximal luminosity is a staggering 150,000 times higher. Interestingly, the star's temperature is not that great, considering it ranges from 3,400 to 3,800 Kelvin, which corresponds to the red spectral band. There are barely predictable processes running in the unstable outer layers of the star that are capable of elaborately changing the object's luminosity. The main pulsation period of the star is approximately 420 days, but less distinct cycles of longer and smaller periods can be singled out too. Besides, unpredictable flares and dimming of the star can be observed from time to time. Because this star is so unstable, it is extremely difficult to calculate the distance between us. According to the estimates offered by the Coriolis satellite in 2020, the distance between the Sun and Betelgeuse is anything from 500 to 650 light-years. According to today's notions of stellar evolution, Betelgeuse would have formed around 8.5 million years ago, and its original mass wouldn't have been over 20 solar masses. It its life cycle would have started in a giant cloud of interstellar gas that would have been gradually compressed and heated up by gravity forces. That is how the protostar, the progenitor of Betelgeuse, was born. At a certain point, the temperature and pressure in its interior reached high enough values to unleash a chain reaction of hydrogen transforming into helium. Moments later, the thermonuclear interaction consumed the entire astronomical body, and a new star flared up in the night sky. This is how the longest period in the life of any star begins, the main sequence stage. Throughout this time, merging of hydrogen atoms' nuclei that produce helium is the main energy source for them. Admittedly, the heavier a star, the faster this process runs. Life expectancy of massive stars like Betelgeuse is a measly several million years, whereas red dwarfs remain active for billions of years. Either way, over 90% of a star's life passes in the main sequence stage. Gradually accumulating, helium is drawn to the object's center to form a helium core. What happens to this star next depends almost entirely on its mass. For example, stars with masses not over 20% that of the Sun do not go supernova at the end of their existence. Unlike more massive stars, having eventually run out of almost all of their hydrogen, they slowly turn into blue dwarfs, hot and comparatively small astronomical objects. However, the minimal time it takes to complete this transformation is around 1 trillion years, which is 72 times the assumed age of the universe, which is why it is doubtful that any blue dwarf will be discovered today. After hydrogen supplies are depleted, thermonuclear reactions in the star will stop and it will become a white dwarf made up of 99% of helium. Ahead are trillions of years of slow fading and cooling until a tepid black dwarf is left instead, which is barely visible through telescopes. If an object's mass lies in the range from 0.2 to 8 solar masses, its evolution goes through more elaborate processes. Helium, which is produced as a result of thermonuclear reactions, adds to the star's core while gravity forces compress it and heat it up more and more. At a certain point, there occurs a reaction of helium nuclei merging, which produces carbon. The star begins to expand, its radius grows as well, and the temperature of the outer layers drops. In this case, the object turns into a red giant or subgiant. Comparatively light stars with masses not exceeding 50% that of the Sun cannot sustain conditions necessary for the chain reaction of helium and carbon. Transformations like these are quite irregular in such objects. As for heavier objects, reactions occurring in the star's core may run longer and produce not only carbon and oxygen, but also heavier elements, like nickel and iron. Eventually, the star sheds its outer layers, and what is left is a white dwarf enveloped in a planetary nebula. If the initial mass of the original star wasn't more than half that of the Sun, it will mostly be made up of helium, with just a small ratio of heavier elements in its composition. If, on the other hand, the star was heavier than that, the white dwarf would be mostly made up of oxygen and carbon. However, with the original star having been heavy enough, it will include neon, magnesium, and even iron. Evolution of massive objects has its laws. The heavier a star, the more massive its core. With the mass of a star 8 or more times that of the Sun, its core might get over the so-called Chandrasekhar limit, which is 1.4 times the mass of the Sun. In this case, forces of internal electromagnetic repulsion are not strong enough to compensate for gravitational compression. It takes a few seconds for the core to shrink, pulling the outer layers in its wake. The exceptionally powerful compression heats up the core to temperatures of hundreds of millions Kelvin and literally crams electrons into atoms' nuclei. This turns part of the electrons into neutrons and produces great amounts of neutrinos. Even a dense material like that is not able to hold back the most elusive particle in the universe. In a few seconds' time, neutrinos break away from the collapsing star and escape, taking some thermal energy with them. As a result, the star experiences extremely powerful internal pressure, as the closely packed protons repel each other with a great force. That is why the core goes on to expand as rapidly as it shrank a few seconds previously, and this produces a tremendous shockwave in the material surrounding it. As a result, a tremendously powerful explosion occurs, which is capable of hurling the star's outer layers enormous distances away. Its flames can unleash reactions that are impossible anywhere else. That is how heavy elements are produced, like gold, lead or uranium. The nebula formed as a byproduct gradually cools off and disperses to form separate clouds, which are later compressed by gravity forces and transform into new stars and planets. Where the star has been, there remains a tiny but extremely heavy object referred to as a neutron star. If the original star's mass was over 18 to 20 times that of the Sun, on explosion, its core is supposed to shrink to form a black hole, a bizarre object that distorts time and space around it. Mathematical modeling shows that particularly large stars with masses over 100 times the mass of the Sun may hypothetically be destroyed by the blast completely. In this case, all the material they are made up of will be scattered by the shockwave many light years around, or else be transformed into extremely powerful electromagnetic radiation. An electromagnetic impulse from a supernova is capable of covering hundreds of light years. At first, the radiation is characterized by incredible force, annihilating all living things on its way. However, with the covered distance growing, the density of the flow decreases and the lethal rays gradually disperse in space. Estimates show that a star similar to Betelgeuse may be a threat to anything within the radius of up to 100 light-years. It is absolutely impossible to tell when this star will go supernova, but it is likely to do so in the nearest 100,000 years. According to some estimates, Betelgeuse may flare up as brightly as the full moon. The dying star will remain the dominating object in our night sky for a while, and then will gradually fade. The object will not be visible to the naked eye anymore, and only the most powerful telescopes will be able to distinguish the radiation emitted by the tiny neutron star. If the mass of Betelgeuse is actually bigger than is assumed now, it may leave a black hole after going supernova. In this scenario, the energy flare will be by far smaller and the sight much less impressive. Either way, there is no threat to the Earth. Betelgeuse lies too far away from the solar system, and a gamma-ray flare that will accompany the supernova will not cause us any harm. The material ejected by the explosion will reach the environs of our system only in 6 million years. Its speed is estimated to be around 13 kilometers per second and will be thwarted by solar wind before getting as far as the inner areas of the system. "650 light-years away from the Earth, there lies IRC plus 10-16, a majestic star also known as CW Leonis. Its radius at its pulsation peak may reach 560 times that of the Sun, which is about 2.6 times the distance from the Earth to our parent star. With CW Leonis hypothetically placed in the middle of our system, all the planets as far as Mars would find themselves under its surface, which would even brush the inner boundary of the asteroid belt. Incidentally, the star's mass is not that great, roughly 1.5 to 4 solar masses. Its surface temperature is just 2,300 Kelvin, or about 2,000 degrees Celsius. But due to its impressive dimensions, the star emits on average 8,500 times more energy than our Sun. Like any other red giant, CW Leonis is in its final life stage. Its age hasn't been defined precisely, but it is estimated to be several billion years. It is assumed that in its salad days, CW Leonis was a white-blue star with a mass 3 to 5 times that of the Sun. However, by 1 billion years ago, a great part of the celestial body's hydrogen had burned out and transformed into helium. Slowly settling in the star's center, the helium ousted all the remaining hydrogen and formed a scorching hot core which did not participate in any thermonuclear reactions. This process typical for all stars whose mass is close to that of the Sun, is the starting point for a star's transformation into a red giant. The star's inner pressure causes it to expand to great proportions, which renders the outer layers more rarefied and unstable. The space object's diameter grows to be dozens of times greater, with its color gradually assuming a blood-red hue. A thermonuclear reaction still takes place in the star's depths, which causes the pressure and temperature of the stellar plasma to increase. At a certain point, this unleashes a chain reaction of nuclear fusion, where helium nuclei are transformed into carbon. This is the so-called helium flash. It is a complex, multi-level physical process that dramatically transforms the star's inner structure. With its core incredibly heating up, its outer layers, on the contrary, cool off and darken. There are currently great amounts of carbon in CW Leonis, but its mass is insufficient to hit the next level of nucleosynthesis. As a result, the thermonuclear combustion in the object's interior becomes unstable. The stellar matter gradually cools off and shrinks under the influence of gravitation. This heats up the star's interior again, and the reaction is unleashed with a new force. After receiving a new portion of thermal energy, the stellar matter expands again, and the combustion dies down. It is assumed that this cyclic process underlies the occasional changes of the star's luminosity. CW Leonis has a 649-day pulsation cycle, and with the luminosity at its peak is 11,300 times brighter than the Sun. With the luminosity at its lowest, meanwhile, the object emits 6,250 times more energy than the Sun. At the moment of contraction, the upper layers of stellar matter partly detach themselves from the star. This forms a carbon-oxygen gas nebula that the star is enveloped in. According to some estimates, CW Leonis loses 4 times 10 to the power of 22 tons of material every year on account of this process, and amount approximately 7 times the mass of the Earth. Observations show that the circumstellar nebula is not less than 69,000 years old, and its mass is about 1.5 times that of the Sun. As for its size, it reaches 84,000 astronomical units. The nebula has an elaborate structure with bulges and pockets of gas, as well as half-arcs and irregular rings. It is posited that these formations appeared due to magnetic activity and stellar wind generated by the unstable star close by. The chemical composition of the cloud CW Leonis is shrouded in is of great interest to explorers. Spectral analysis data reveals it to contain around 70 different chemical compounds, for example carbon dioxide, water and ammonia, to name but a few. There are also quite a lot of elements from the upper part of Mendeleev's periodic table, right down to iron. CW Leonis may have had planets in the past, but they appear to have been swallowed up early on at the stage of expansion. In any event, years of observations did not reveal distinct traces of their existence in the past. What was registered was subtle changes in the star's orbit back in 1994, and more recently in 2017, mysterious shifts of matter were detected in the cloud of gas and dust enveloping the star. Some small red dwarf orbiting the giant could well account for these phenomena, although attempts to detect its radiation have so far been unsuccessful. This could be due to the nebula close by, which disperses and reflects the energy flow from sources of light located nearby. This phenomenon camouflages any objects in the immediate environs and prevents them from being accurately recognized. The mass of CW Leonis's hypothetical stellar companion is assumed to be definitely smaller than that of the Sun, and it should take it approximately 100 years to complete a full orbit around the giant. Another outstanding feature is the comparatively high water content in the star's environs and envelope. At first, it was posited that the star would melt and swallow up icy comets as it expanded. However, observations carried out in 2009 showed the temperature of some spectral lines to reach 1000 Kelvin. which is possible only on condition that water vapor forms actually in the upper layers of the giant. This fact did not fit in the model of red giant's structure accepted at the time, according to which all oxygen in stellar matter necessary for water synthesis must be used up completely to produce carbon monoxide. A new hypothesis was put forward to account for the witnessed phenomena, which stated that molecules of silicon oxides and carbon are destroyed by a powerful ultraviolet radiation. After that, the released oxygen reacts with hydrogen and there forms scorching hot water vapor. The weakness of this hypothesis is in the failure to account for the source of ultraviolet radiation. Reactions like that may occur only in rather high temperatures, that is, within stellar matter. However, it is practically impervious to cosmic rays. This paradox may be explained by yet another assumption. Since the star is unstable, large ruptures and low-density areas occasionally occur on its surface, where ultraviolet radiation is not blocked out that effectively. The water vapor's overall mass in the star's atmosphere and outer layers is estimated at several quintillion tons. Enormous though this figure may seem, in fact, water accounts for just around a billionth of the star's overall mass. According to today's notions of stellar evolution, being a red giant, CW Leonis is in its autumn years now. It will deplete its stellar fuel in the next 10 to 30,000 years, after which it will discard its outer layers following a powerful explosion. It will transform into an incredibly hot and dense space object, a white dwarf. Its mass will be roughly 80% that of the Sun, and its temperature will reach several million degrees in the first seconds after the transformation. However, with no energy source, it is destined to slowly and irrevocably fade in the course of billions of years to follow. Eventually, the celestial body will be almost invisible against a background of cosmic emptiness when it becomes a mysterious black dwarf. But this will not happen anytime soon. Until a short time ago, it was UY Scuti that used to be considered the largest star known to mankind for a long while. Located 9,500 light-years away from the Sun, the star is so staggeringly enormous that it would cover areas beyond Jupiter's orbit were it placed in the center of the solar system. Its radius may reach 1,900 those of the Sun, and its volume may be over 5 billion times that of the Sun. However, recently a new giant has claimed the title of the largest star in the known universe. It is known as Stephenson 2-18, or RSGC 2-18. The star lies approximately 20,000 light-years away from the Sun and is part of the open cluster Stephenson 2. Although according to some scientists, this space object should not be associated with the Stephenson cluster, as it wouldn't be accurate. Either way, Stephenson 2-18 is located in the Scutum constellation and continues to bear its original name. The star itself was catalogued in the All-Sky database back in the 1990s, but giant clouds of cosmic dust largely interfered with observation of the star clusters in the Scutum constellation, obscuring them from any observer anxious to find out more. Only in 2020 were scientists able to acquire data about its size, and the information proved to be astonishing. According to some estimates, the radius of Stephenson 2-18 may reach up to 1.5 billion kilometers, which is 10 times the distance from our Earth to the Sun, or 2,150 times the radius of the Sun. This means that the supergiant's volume should be about 10 billion times that of the Sun. Placed in the center of the solar system, Stephenson 2-18 would easily swallow up Saturn, along with all of its rings and moons, to say nothing of the terrestrial planets. Interestingly, it would take light almost 8.5 hours to travel the length of this gigantic star's equator. This is the same time it takes sunlight to reach Pluto at the remotest point of its orbit. The supergiant's luminosity is estimated to reach 440,000 times that of the Sun, although its surface temperature is comparatively low at about 3200 Kelvin. This is about 2 times as little as that of the Sun and corresponds to the red band of the light spectrum. This is the reason why Stephenson 2-18 falls into the category of red supergiants. Also, this relatively low temperature implies that most of the star's radiation is in the visible and thermal spectra, with amounts of deathly ultraviolet and X-ray types of radiation rather negligible in comparison. It may seem strange that in spite of its impressive dimensions and sufficient luminosity, Stephenson 2-18 cannot be seen from the Earth with the naked eye. But this has to do with its low surface temperature as well as clouds of stardust and gas shrouding the giant star, thus concealing it from observers on our Earth. They absorb and disperse the star's light, and this poses difficulties for studying the object. The mass of Stephenson 2-18 still remains to be gauged. However, supposing its inner makeup is similar to that of UY Scuti and other supergiants, it should be anything within 20 solar masses. If it is the case, the average density of supergiants like that must be extremely low and almost equal to the density of the Earth's atmosphere at a height of about 90 kilometers above the sea level. That is practically on the border with space. It is really amazing that thermonuclear energy, that is the kind of energy that gives a glow to a star, is still sustained in such conditions. Supergiant sizes are so mind-boggling that these objects are hardly steady. Most of them are variable in terms of their luminosity, and as a rule this variability is unpredictable. No wonder, as the overwhelming majority of supergiants are in the final stages of their life cycles, which means that they may go supernova literally at any moment. According to the contemporary scientific concepts of stellar evolution, it is stars with original masses from 10 to 40 that of the Sun that qualify to become red supergiants at a later stage of their existence. Thermonuclear reactions in their interior rapidly burn out all hydrogen, thus turning it into helium. After that, fusion reactions of helium, carbon, oxygen and lithium become the chief energy source of the star. Life expectancy of stars of this kind is comparatively short, just a few million years. As it evolves, the prospective supergiant rapidly expands in size and loses its mass on account of strong solar wind. Clouds of stardust and gas surrounding the original star are quickly absorbed by the new star, which keeps swelling way beyond its original size at an astonishing rate. However, its own solar wind creates a new nebula around the star. On account of the short lifespan of this kind of star, no planets can realistically originate in this nebula. Eventually, the supergiant explodes. Following the supernova or even hypernova event, the outer layers of the star are hurled away and then gradually cool off, forming a nebula. As for the former core, it becomes either a neutron star or a black hole depending on its mass. By the way, feel free to see our previous videos about dwarf stars and supernovae. A hypernova event is accompanied by a high-energy X-ray burst, powerful enough to eliminate any life within the radius of several light-years. Luckily for us and the Earth, all supergiants identified by scientists so far lie considerably further than that, so we seem to be safe from those. Due to active radiation of charged particles, the rotation of stars of this type gradually slows down, and eventually their outer layers practically grind to a halt. The core of the star, meanwhile, continues to rotate quite unabated, and there may be a substantial difference between the speed of the core and that of the outer layer. Taking into consideration the high luminosity, low temperature and impressive dimensions, on balance it is safe to assume that the habitable zone of Stephenson 2-18 should be really huge. Its middle should lie approximately 663 astronomical units away from the star's center. In other words, 20 times the distance from the center of the Sun to Pluto's orbit. And as for the area of the habitable zone, it is expected to be 1 billion times that of the Sun. Scientists do admit of the possibility of the existence of planetary systems around supergiants. But what with these stars' short lifespan and unstable conditions, the chances are almost negligible. At any rate, no confirmed exoplanets have so far been discovered in the environs of one. Stephenson 2-18 lies so far away that its light travels to our Earth for 20,000 years. For all we know, at this very moment its core might be shrinking to form an extremely dense neutron star, with red-hot shards of outer layers flying away in all directions to become part of ice-cold space. But mankind will be able to find this out only in a very distant future. There are stellar nurseries richly scattered across the galaxy, with some of them comparatively modest in size. Others stretch for tens and even hundreds of light years. These are vast nebulae made up of interstellar gas and dust being inexorably compressed by gravity forces. Most of these tremendous clouds are barely visible against the abyss of space, but some of them can be seen from the Earth with the naked eye. One of these structures is the Orion Nebula, located 1,344 light-years away from the Earth. It is the middle object in the so-called Sword of Orion, a clearly visible line produced by three relatively bright light sources. Due to its large size and comparative closeness to the Earth, the nebula has been attractive for scientists ever since the early days of astronomy. It is hardly surprising, therefore, that this great structure is one of the best-studied space objects. It was the Hubble Orbital Space Telescope that beamed back first images of the Orion Nebula back in 1993, where the rich diversity of its colors can be appreciated. Most of the material was of a reddish or bluish-purple hue, while unusual bright green lines of some peripheral areas were revealed by spectral analysis. This phenomenon perplexed scientists for a long time, as the observed radiation did not demonstrate any chemical element known at the time. There was even a hypothesis that was put forward about there being a hypothetical element nebulium, argued to be not present on our planet, but allegedly amply scattered across clouds and space. However, with the advancement of science, it turned out that the light was emitted by extremely rarefied and deionized oxygen. This discovery accounted not only for the bizarre illumination of many nebulae, including our Sun. There are currently not less than 3,000 stars discovered in the Orion Nebula to date, as well as giant clouds of interstellar gas and a great number of protostars. All this amazing diversity of space objects is concentrated in an area of around 23 light-years in diameter, all of them continuously and elaborately interacting with each other. The overall mass of the material concentrated here is around 10,000 solar masses. Looking at the Orion Nebula closer, we will notice several clearly defined areas. The most outstanding of them is trapezium, also known as Theta 1 Orionis. It's an open star cluster about 300,000 years of age, made up of 8 main components. Some of them are binary stars, others have no companions. The brightest and most noticeable of the trapezium stars are 4 stellar systems designated by letters of the Latin alphabet. Located close to each other, they lie within an area about 1.5 light-years in diameter. Each of these objects' mass is within 15 to 40 solar masses, which means that these stars are quite young and hot. Theta 1 Orionis C is the most massive, as well as the brightest star in both the trapezium cluster and actually the entire nebula. It is a white and blue main sequence star with a mass roughly 40 solar masses, whose radius is 8 times that of the Sun. The object's surface temperature is approximately 45,000 Kelvin, and its luminosity about 250,000 times higher than that of the Sun. The radiation of Theta 1 Orionis C illumines virtually all the nebula around it, but there is hardly any interstellar gas in its immediate vicinity. This is the case due to the fact it is typical for objects of this class to experience exceptionally powerful stellar wind that scatters rarefied material far off. Having traveled a few light-years away from trapezium, we will see another remarkable system, which is Theta 2 Orionis. It is made up of 3 gravitationally bound stars located close to the so-called Orion bar, an extensive feature of hot gas emitting bright light. It was impossible to study this area for a long time on account of dense clouds of dust, and thanks to the James Webb Telescope, more detailed images of this region have been beamed back to us. The first component of Theta 2 Orionis is just slightly less massive and not as luminous as the trapezium's biggest star. As for its surface temperature, it measures about 35,000 Kelvin. The second component of the system is 15 times as massive as the Sun and 12,000 times as bright. The third component is as heavy as 5 solar masses, and its temperature almost reaches 14,000 Kelvin. However, it wasn't just bright stars that caught the researchers' attention. James Webb's infrared cameras allowed it to detect previously unseen objects, hidden deep within the clouds of gas and dust. Thanks to the telescope, about 180 so-called proplids have been discovered at the heart of the Orion Nebula. These are dense, dark protoplanetary disks surrounding stars that are still in the process of formation. One of these is Orion 294-606, a young protostar about 1 million years old, surrounded by a gas and dust disk about 300 astronomical units in diameter. Thanks to its being edge-on to Earth, we can observe its structure and size. It is expected to hit the main sequence phase in a few million years, and it will be accompanied by a system of several exoplanets and possibly their satellites. The night sky of these future celestial bodies must be a truly fantastic sight. Just imagine a multicolored luminous veil with the glow of a multitude of close and bright stars far more numerous than those seen from the Earth coming through. And now and then tremendous swirls of glowing gas cover half the sky, turning the night into translucent twilight. If we fly a little further and examine the wider region, we see that the bulk of the nebula is filled with scattered gas. The central part of the cloud is filled with highly ionized hydrogen, which actively absorbs high-energy stellar radiation. The temperature of this gas can reach 10,000 Kelvin, but it falls sharply towards the edge of the region. Temperature and pressure contrasts, as well as the collision of stellar wind streams, set material in space in motion, creating tremendous currents and vortices. According to calculations, some of them can reach speeds of up to 50 kilometers per second, and their size can be greater than the solar system. Also, in some areas of the nebula, thin strands stretching for several light years have been detected, consisting of relatively cool molecular hydrogen, without mixtures of methane, ethane, and water. Further out, we will see that the central region of the Orion Nebula is enveloped in a vast cloud of cooler, denser gas. The cloud of bright stars and the luminescence of ionized hydrogen intricately intertwine here, creating a beautiful multicolored curtain of light. Hidden behind it are hundreds of space objects, invisible in the optical range. But the infrared cameras of today's telescopes allow us to see through the veil of interstellar matter. By combining data from different sources, astronomers have discovered about 700 protostars at different stages of evolution within this region. Their concentration is noticeably lower than in the central part of the nebula due to the lower degree of gravitational compression of the interstellar gas. The absolute majority of these objects are very young by space standards and are still in the process of formation. According to modern concepts of stellar evolution, new stars form during gradual gravitational compression of large clouds of interstellar gas. Typically, as a result of this process, giant nebulae split up into a number of closely grouped gravity centers, which soon turn into protostars. Such clusters are called stellar nurseries, or more scientifically, regions of star formation. At a certain point, the internal pressure of the compressed gas compensates for the gravitational forces, bringing the protostar to a state of temporary equilibrium. The remaining material swirls into a giant vortex disk, with some of it gradually absorbed by the future star, and the rest of it, by contrast, expelled far beyond the boundaries of the nascent system. The growing magnetic field of the young star also plays its part, as ionized particles accelerate through its field lines and then rapidly escape from the vicinity of the object. It has been calculated that such flows can reach speeds of up to several hundred kilometers per second. As they collide with the gas clouds surrounding them, they create large-scale vortices and hemispheres called Herbig-Haro objects. In the process, part of the kinetic energy dissipates into light and heat, giving these bizarre structures different colors. In addition, the ultra-fast motion affects the surrounding material, spreading shockwaves across it, which incidentally are also captured by telescopes. Since stellar nurseries contain many closely spaced protostars, each producing several gas emissions, it is not surprising that Herbig-Haro objects exhibit an amazing variety of shapes and colors. Clearly, being essentially the result of a major cosmic collision, they are highly unstable and variable. Herbig-Haro objects rapidly change color and shape, and typically disperse completely over several tens of thousands of years. During this time, they cover between 1 and 3 light-years on an escape trajectory from their parent stars. About 400 such objects have been discovered so far, with their total number within the Milky Way estimated to be about 150,000. Perhaps one of the varieties of this awe-inspiring natural phenomenon is the bullets, hundreds of astronomical units in diameter, also detected in the Orion Nebula. Moving at incredible speeds, they easily pierce thinner hydrogen clouds, creating far-flung shockwaves in them. According to spectral analysis, the frontal parts of these objects contain atoms of iron that glow in the infrared. The bullets are estimated to be about 1,000 years old, and their origin is still a mystery. They supposedly originated from some catastrophic event. Moving on, we will soon find that the Orion Nebula is part of a much larger cosmic structure called the Orion Cloud. It stretches for hundreds of light years, accounting for virtually the entire constellation of Orion in the Earth's night sky. This is where the well-known Horsehead Nebula is located, remarkable for its bizarre shape. It is a dense dust cloud, about 3.5 light-years in diameter, clearly visible against a background of a contrasting scarlet glow. Also close to the Orion Nebula, there is an impressive cosmic structure called the Barnard's Loop. This emission nebula, about 300 light-years in size, came into being about 3 million years ago, after a series of consecutive explosions of mutually close supernovae. After the shock-compressed gas jets mixed together, they produced a gigantic curved nebula, and the glow of several young stars, gathered in an open cluster, made it reddish in hue. For all its beauty, the Orion Nebula is a fragile and unstable object by the universe's standards. Stellar winds and pressure of light from many young stars, as well as gas emissions and turbulent vortices, constantly disperse its material in the surrounding space. The nebula has already lost about 60% of its original material, and in about 100,000 years, it will be stripped of its remnants. In place of the shining multicolored cloud, there will remain an open star cluster similar to the Pleiades. For a time, the young stars forming it will move together, but eventually, each will find its separate way through the vast expanse of the boundless galaxy around. The number of stars in our galaxy alone is several hundred billion, while the number of stars in the entire universe is pretty much impossible to count. Each of them is unique, from a faintly glowing red dwarf to a blue giant searing everything around it. However, we see only a small fraction of a percent of this incredible diversity, which means that there are many more amazing discoveries ahead of us. And let's keep in touch.